one in the industry, we've come to realize that hydrology has an influence on almost everything else we do in the design of a solar site. It helps to set design constraints, ultimately helps determine project cost. Our perception is that hydrology is finite mathematical science, never changes, never varies, never wavers, because we're engineers and we're using engineering calculation. But hydrology is very much an art.
Today on the show, we've got a lot of special content on the topic of hydrology. Now, what is that? Well, we'll get to that in a moment. First, I'm your host, Christoph Brun. Joining me, as always, is...
Prahlad Shivshankran.
Russell Hamilton.
Well, I already made a comment about your sweater last show, so I can't do that again. What about you, Russ?
So I was going to bring it up.
Sprint cars?
Not sprint cars, although I'd love to. Off-season, but they're racing in Australia, great. But what I was going to talk about is I shoot pool league. And my pool team, it's 8 of us, 7 folks from EVS, and then my best friend. And we won our pool league the fall season, and we got trophies and plaques and everything like that. So, it's pretty cool. We kicked off our second season. Our first night was on Monday, and we got crushed. I think it's like that championship hangover, where we got murdered. Ouch. It was bad.
Do you play 8-ball or 9-ball? Okay.
Yep.
Is there... I'm assuming there's 9-ball leagues too as well.
Yep.
How does it work with the team element, team aspect? How does that, you have 7-8 people. I mean,
so we have
not all playing at once.
5 shooters a night.
Yep.
We shoot in 2 tables. Your skill level, there's some complicated algorithm that they use to calculate your skill level. Anywhere from a 2, 3, 4, 5, 6, or 7.
Where are you ranking?
I'm at a 3 right now.
Okay.
Which
better than 2.
Should be higher.
Well, it should be 4.
We'll get there. And your opponent, you flip a coin, and if you win the coin toss, then you okay, I'm going to put Prahlad up, and he's a 4. And they go, okay, I'm going to put a 4 up. We're going to put our 4 against him, or our 7, or our 2, whatever.
Sure.
And that's how it happens. And then depending on your level, so if you're you're a 2 and you're shooting a 7, the 7 has to win 7 games in a row, or 7 games, and you only have to win 2 to win the match.
Oh,
and so there's a handicap in there that tries to level it out.
Interesting.
Wow.
Yeah.
Huh. We better sign up.
Yeah, no, I'm pretty bad, but I'll sign up.
Can't be worse than a 2.
No, I can't be
there
worse
is no 1.
Don't go down to 1.
Well, today on the show, we've got Mr. Byron Hinchey. He's going to be telling us all about the world of hydrology, what that means for utility scale solar. Byron, maybe just introduce yourself. Let us know who you are. What's your background?
Oh, my background. I went to college at Tennessee Technological University way back in the day. A couple of years in, sophomore, I saw a lot of my friends, classmates, applying for what today we would call an internship. So I thought, man, sounds good. I'll do that as well. Maybe I graduate with some experience under my belt and let me get a job in the future. So during the course of my college career, I ended up working for 2 years for the U.S. Geological Survey. I did things like install stream gauge stations, conduct stream flow measurements, got to do that some during flood events, either from a cable car or from a moving boat, and some cool stuff for a young guy to see. And survey high water marks after flood events passed. So I did a lot of work with flood data, if you will. And that really got me interested in water resources in general. I eventually graduated with a Bachelor of Science degree in civil engineering, but I had 2 years of work experience under my belt by the time I graduated. So back in those days, we called it the Cooperative Education Program. So you went to school for a year, you worked for a year, back to school for a year, back to work for a year, and so forth, until you graduated. I had naturally had a job offer from the U.S. Geological Survey to come back after 2 years intern. You always hope your interns come back for a full-time job. But I was recruited into private practice because one of my coworkers at the Geological Survey had left government service and joined a local consulting firm. So I was recruited in both the government sector and the private sector. Since I had done the government sector for a couple of years, I thought, well, let me see what the private sector looks like. That was kind of a career-changing decision, if you will, or a career deciding decision, because that internship, number one, steered me toward water resources, but number two, going into private practice has me sitting today somewhere completely different than I would have had I gone back to my employer into government service. Mm-hmm. For example, if I'd stayed with government service, I would have been retired with a full federal pension.
Well,
so what you're saying is,
but you wouldn't be on the podcast right now, or maybe you would, and you'd be on the golf course right now or something.
Well, hopefully, what you hope for is that you retire, you draw that full government pension, and you're still working for that consulting firm making the big bucks.
Can you tell the listeners what exactly is hydrology?
So in solar in particular, we use the term hydrology, maybe something as an umbrella term for the entire process of determining eventually the depth and velocity of water for a rainfall event. And then using that information, we compute Scour. So that process of determining depth, velocity of water, and the Scour that it may generate, that really we lump all together under the term hydrology. That's the solar market in particular. Now, in reality, you go outside of solar or go maybe back to the academic roots, if you will. Hydrology is really the estimation of stormwater runoff, which is generated by a rainfall event. So to do that, we delineate drainage area, we delineate land use types, we look at soil groups, soil types, infiltration rates, and we look at how long it takes water to flow or to propagate downstream in a rainfall event. We have to select a rainfall event, and there's a million options. And then we put all that information into a hydrologic model. We apply the rainfall event to the drainage area with all the parameters we define. And that hydrologic model calculates for us the runoff, which is a peak runoff and the volume of runoff and the shape of that hydrograph, or over what time base maybe that water rises and that water falls. The other component of hydrology in solar is actually the hydraulic component. So in really, hydrology is the calculation of that runoff. How deep it gets really is called hydraulics. Mm-hmm. So hydraulics takes that runoff, applies it to the terrain, to the elevations, and the roughness of that terrain, and then calculates through a variety of equations the depth and the velocity of the discharge that's generated by the hydrology. But in solar, in the end, I'll leave you with this, in solar, we largely combine the hydrology component, the hydraulics component, both, for the most part, into a two-dimensional model, and we call that hydrology.
I already have a lot of questions.
Yeah, a lot of questions.
Could you define what Scour is? Yeah. I don't know what Scour is. I'm just a lowly electrical engineer. So
I would define Scour as the effects of the erosive forces of velocity of the water on the land mass. So Scour is, in the solar world, Scour is not how much sediment runs off your site and fills up your sediment pond or your detention basin, but Scour is the hole that's formed as water runs through your equipment, around your piles, holding up your equipment, and typically on the downstream side of a pile, due to the eddy forces of water rushing around that pile, the depth of it and the velocity of it dictates how much of a hole you will have on the downstream side or the downhill side of an obstruction like a driven pile.
And this is part, as far as my background goes in the structural world, this is one of our main design parameters, especially like a desert site, very arid, no vegetation. It can get real pretty fast. I know there was a project that we worked on in-house that only a year into service had a major rainfall event. The scour on the piles was, multiple feet deep. That's how much erosion occurred. And I don't think this was a 100-year storm event either. This was like a 50-year storm event. And in the desert, as Byron can tell you, I'm sure that a small amount of rain, just because of how dense the soil is and how arid it is, you can get flash flood events very quickly. And so if you ever see rain like out in Phoenix, out in the countryside, it will just, a little bit of rain can suddenly turn into a pretty massive water flow event.
Is that why you generally have a basin to capture all that and kind of put it back? Or like what's the, like, I guess?
Typically we calculate hydrology, the runoff, and then the effects of that runoff on water depth, velocity, and the scour it creates. We do that at a watershed level. And then our civil designers, for the most part, using a different model, a little different approach, they will take and model the runoff from that design facility based on the requirements of the local AHJ authority having jurisdiction. They will decide whether they need a basin, and if so, how large it needs to be to control whatever storm events that the AHJ requires. So there are areas in the country, there are some of our studies, we don't have basins. The runoff goes as it would naturally go, whatever direction it would naturally go, and we do not have a requirement for controlling the future runoff. And in most cases, we're assuming that that future runoff is not going to be any worse than the existing runoff. And we show that a lot in our modeling because a lot of times we're preparing a project in design that's got a good vegetative grass cover. And so we may actually, in some cases, reduce runoff in the design condition because we're improving the stability of the soil, we're improving the amount of infiltration, or we're improving the drainage, or changing the slope of the land and so forth. So we do basins in part for sediment control on most sites, but a lot of times those sediment basins are taken away at the end because we don't have a requirement to do the control of quantity and quality long term.
So with that erosion, so I'm just trying to understand, do you put it, so how would you have to put back the soil once it's eroded near these piles? And is that why that you have those basins, or is?
So a lot of the times, I would say most of the time, we have sediment basins on site to control erosion during construction.
Oh, okay.
Once construction's complete, if we've got a vegetative cover, we generally consider then that the erosion is largely minimized. We can excavate that basin, take the soil that's eroded into the basin, we can take that out, get rid of it, reuse it on the site somewhere, leave that basin for long-term control of water quantity or quality. We almost have a transition point then, post-construction, in between the need to control erosion and the need to control scour. So we typically don't design basins for scour conditions and what sediment may transpose downstream in a rainfall event based on scour. Sediment basins are normally to control the runoff during construction, or the sediment leaving the site during construction.
I feel like hydrology is kind of the most fundamental part of the civil engineering aspect of a solar project. A solar project, utility scale solar project, is definitely an electrical project, but it is practically the biggest civil engineering project you can work on in terms of land volume as well. From my side of things, hydrology, it's really an iterative process for all disciplines involved because we set the pile heights based on the hydrology runs. Our pile design is based on hydrology factors, scour being namely one of them. So Byron, in the current state of the civil side of solar projects, how would you characterize where hydrology is now and challenges and its relationship to the civil aspect of solar projects?
So I think we typically, number one, in the industry, we've come to realize that hydrology has an influence on almost everything else we do in the design of a solar site. I would say design and construction and maybe even maintenance of a solar site. In the past few years, we've put more and more importance on hydrology being something we do and get a handle on, get an understanding of at the very beginning of a project. So we're oftentimes doing our initial hydrology models before we do anything else on the design side. So the importance is it typically flood risk. It helps to set design constraints, ultimately helps determine project cost. We take a look at the existing conditions and do a hydrology model, which has a bearing on everything else civil because it it dictates really how much site work is needed to minimize that flood risk. We look at the design condition or the as-built condition. We're running a proposed condition model or an FG of the future conditions, a future grade model to determine how much that water is expected on site in perpetuity if we implement a proposed design. So there will always be water on site. It's a matter of how much and where. In guiding, directing design, already mentioned cost of construction is really driven by the snowball effect that starts with hydrology. Mm-hmm. So for civil, the cost of earth moving to get the grade just right. In electrical, maybe that's the elevation of equipment. In structural, maybe that's the depth of piles, the length of piles, how much pile reveal height we need, and elements like that. So for the most part, I think hydrology, from my perspective, I hope at least, that hydrology really drives almost every other aspect of the design process that we do for a utility scale solar.
Yeah, it absolutely does, honestly. And, just speaking on what I can say about structural is, let's say, for example, the hydrology run and the grading are saying we want to do 6 inches more of pile reveal, or just basically the parameters.
Yeah.
Thinking about even adding 6, maybe even 3 inches of reveal on a pile and multiply that change by 50,000, 100,000 piles on a site. Not only that changes the load application height for us, we move everything up 3 inches. If the high water level goes up 3 inches, same problem with the scour. How deep is the scour? Then these design parameters suddenly, they could increase the depth of your steel, like he was saying, or also upsize the thickness or the material strength or parameters of the pile shape. And these things, they spiral kind of exponentially out of control. And so these runs are just, they're so fundamentally important for all of the civil engineering aspect. And now correct me if I'm wrong. Now, what is the average time? Maybe there's not an average time, but these models take like 10, 15 hours to run. They're probably the most computationally heavy processes that we do in solar. Maybe there's studies that are also rivaling this too. Grounding studies too. But yeah. I mean, I've heard these runs take so long. They're so computationally demanding.
And what softwares you're using as well? Because I don't even know what software go into hydrology.
That kind of dovetails into the maybe the conversation of challenges.
Yeah, definitely.
So I would say the broad scope, and I'll answer your question in a second, within the broad scope of challenges, first and foremost, when we're looking to set up a data, a huge challenge is the lack of data, or pardon the term, crap data. We've got data, but it's really not very good. Sometimes we're having to do models with federal data collected at such a resolution that we're working with a terrain surface that we would call a 10-meter terrain. So a data point every 30 feet defines that terrain surface. That's extremely coarse. And, we're blind throwing at the dartboard. We get an answer. Can you put a lot of faith in that answer? In my opinion, no, not very much. Rarely do we have information on culverts. A lot of projects start with a surveyor out in the field running an ALTA or something. And I apologize, I cannot tell you what the acronym ALTA stands for. I'm not a surveyor, but we start with survey information a lot of times, but it never has culvert information in it. So culverts through the site, around the site, upstream, downstream, the effect of culverts can keep water from getting to your site, or it can back water up from downstream onto your site. So a lot of times we have to guess, or we've got to go and collect that culvert data sometime later during the design process. So a challenge then is, how do we put together an accurate model that guides design in a fast-paced design world? So the time between design and delivery sometimes leaves very little time for that modeling effort beyond that initial model setup for existing conditions. So as we start going through the design process, sometimes to meet schedules, we're doing the civil, electrical, structural, all of those design elements, hand it to a modeler sometimes on a Friday afternoon and say, hey, can I have the results by Monday? Sure. I don't mind working this weekend. But to your answer, or to your question on the time it takes, it really varies, Chris. Some some models will run in a couple hours. Sometimes those are even proposed or finished grade model runs because there's limited culverts. Maybe the drainage area for that site is small. And so it's just not that computationally complex. But then we do have sites, for whatever the reason, where it may take 18 to 24 hours for a single model run. So a lot of times our contracts or our clients, they want multiple storms run through the model. Maybe they want a 100-year storm, and they also want to see what happens in a 25-year storm. Some clients want to see both a 10-year, a 50-year, a 100-year, a 500-year. If you start getting into a model that takes 12 to 24 hours to run, and you need to run 4 iterations for different design storms, all of a sudden now, it can take days and days to get the answers that everybody's waiting for to proceed with design. Last challenge that comes to mind that I think of is really in perception, whether it's internal or external. Our perception is that hydrology and hydraulics, what we call hydrology in the industry, is a finite mathematical science, never changes, never varies, never wavers, because we're engineers and we're using engineering calculations. But hydrology is very much an art, and it starts with the rainfall. It absolutely never rains in reality exactly how we put it into a model. Mm-hmm. We're putting in statistical rainfall into a model, or maybe in some cases, very few and far between, we'll use rainfall from an actual storm event if we can collect it. But in either case, in the future, you're guaranteed that the rain will never fall exactly that way again.
You know, I'm listening to you talk about this. There's a lot of correlations to what you go through and what studies go through.
And I imagine there's a lot of challenges there too to explain that to clients and owners, et cetera, that like this is what we're working with. This is the data. This is the best we can do because of the situation. It's the same in the studies aspect.
So can I ask a quick question, just because I don't know the process of hydrology in a project? When does hydrology take place in a project? Do you follow the same 30, 60, 90 IFC?
So we start at the very beginning. Oftentimes these days, we start before civil even starts or electrical even starts working on the BAM, the buildable area map, because everybody wants to know what is our flood risk. You know, how high is the water going to get? Where's the water going to be? And so today we try to do hydrology at the very beginning. So we're grabbing publicly available data. We're grabbing data that's been provided by the client, if we have any. That would include, of course, the site boundary or the parcels that they owned or leased or they expect to build. And we will put together a model using largely data sets from federal agencies. And so we produce that existing grade model, pass that off to the designers in all disciplines. Eventually, civil, being the coordinator between us and other disciplines, typically civil will come back to us and say, okay, we're approaching the 30%. We've got a preliminary design for 30%. And here is a terrain surface, a designed surface, if you will. Can you run our proposed surface through the model for our 30% submittal? And we will. Sometimes then that comes back and it becomes an iterative process because we need to change a couple of things. We do the same, repeat the same thing at the 30. That we do at the 30, repeat the same process for the 60% and the 90% submittals. Refining the design gets more and more intense when you get to, say, a 90%, because we're really getting into a final design. And if our model shows that with that proposed grading for that final design leaves us with some depths that we really are adverse to our design on the table, then there becomes some iteration back and forth to let's tweak our surface, give it back to us in hydrology. We reground the models, gets back to civil, which eventually which immediately, I guess, filters back out to structural, electrical, and others that we're making small changes. So it is very much an iterative process, but it all starts with that existing conditions model before anybody else really gets to work.
So in my world, in the structural world, there's certainly sites that are better than others. There's soils that are much more structurally better performing, et cetera. What is a good hydrology site? What is a bad one? Are there such a thing? And why is a site good versus why is a site bad?
I would say, number one, from a hydrology perspective, I think that in the industry, owners, developers, engineers, we all try to avoid anything that might look or smell like a floodplain. And so when you think about hydrology, you kind of link that to a FEMA floodplain mentality, which is if there's water, and I know there's going to be water, and it's connected upstream and downstream to other water, I really shouldn't be putting multiple hundreds of millions of dollars into electrical equipment in standing water.
Right.
But sometimes that's solar development sometimes looks a little bit like site development. An owner has a piece of land, and by golly, they want to develop it. And they have an idea they're going to put a solar facility there. So the water's there. We're going to hire a bunch of engineers. They can figure out that water stuff, and it'll be okay. So, first and foremost, let's avoid the floodplains. So that really, though, carries into why is hydrology important, or fail to remember exactly how you asked the question. But in hydrology, we try to, number one, if there's a floodplain or a river system, a conveyance system involved, we are redefining what FEMA may have determined could have been in the 1970s, could have been last year, but we're redefining it using the latest rainfall data and using models that are more complex than was originally used by a federal agency to set the expectation of flood risk. But then beyond that, typically we're looking at all of the minor conveyance systems on a given site, and that site might be 10 acres, 100 acres. Some cases, some of our projects are up into the thousands and thousands of acres. We sometimes have a site that's almost a watershed in size, if you will. And so we're really determining how much water is going to be draining through all those little tributary streams to that FEMA floodplain, in addition to trying to decide how much water is going to be sitting on the high ground, trying to get to those tributary streams to eventually get down to the river or stream to be carried away.
Is that something you do at like a 30% bid support level? It seems like just avoiding floodplains, at least whenever I see projects come in, it's almost like this project has to develop from a 15% all the way to IFC. But it seems like the floodplains is sort of like a qualifying element for a project to even be viable, right? So is that something that EVS does at like a bid support level or interconnection? So we highlight, what you can't actually build on this in this piece of land.
For the most part, owners do a preliminary hydrology study, short duration, low budget, but they hire some consultant to do a preliminary hydrology study before they put that project out for a contractor engineer combination to bid upon that project. In those cases, we're typically bidding on a project using somebody else's information. And I hope we're doing that knowing full well that that was a very coarse preliminary study. Most likely they used all publicly available data. There's no culverts in the models. The parameters were maybe loosely estimated. Maybe the means and methods in some cases wouldn't be exactly what we would want to see in a design level. So I think the industry or the players in the industry are starting to get wise to that and are getting a little bit smarter. In the last year, we've seen a couple of clients that wanted, even at the bid support level, to generate their bid for the owner. They are coming to us and asking us to take that preliminary hydrology and advance it. Tell us what it really looks like, regardless of what the owner thinks it looks like. Take that next turn of the wheel and give us a little better idea of what hydrology we can expect so that we can better refine our bid for that project.
Okay. And another question about...
It doesn't happen a lot, but the contractors that are bidding are going that direction, it seems.
You mentioned a little bit earlier about localized events, and I would think Scour is just like this because you're not going to have perfect rainfall over the entire site. That's probably never going to happen. And we design piles with Scour as a parameter. And we also, in the same, like you're saying, we use building codes that were designed for occupied buildings. And our design loads, the Scour, the corrosion, and also the mean recurrence interval, just like the 100-year storm events. I mean, there are layers and layers and layers of conservatism applied on the structures of these sites. And I think it's the same thing you're saying is like, I think that's one of the biggest opportunities in solar in general is to have a bigger conversation about risk and reliability and to really understand like, okay, well, we designed 50,000 piles for a 1 foot of Scour. We might have Scour on like a few sometime, someday. And this is the gap between how we perform our engineering and how ultimately the bank and insurance is going to respond to it. And there's numerous articles about bankability of solar projects and insurance out there. But it is something that there's a big opportunity here in renewable energy in general, is just to understand these are sites that are built for 25 to 35 years on average. And we design them like they're nuclear plants in relative terms.
I think we'll probably see change once the insurance companies get impacted. I think that's when we would start to see them being, hey, let's get rid of some conservatism.
Right. And there's a trade-off here of premiums paid by owners versus responsible design. Yep. And right now we have kind of the worst of both worlds in a way. I think we're paying high premiums. And if you look, there was just an article on PV Magazine not too long ago. Over half of the total insurance payouts for solar sites, guess what it is? Anyone wager a guess? Hail damage. Hail, not sky. Yeah.
Oh, okay.
Hail, of course. We had a hailstorm. It cracked all the panels. Duh. It wasn't 50,000 piles that had Scour on them. When is that going to happen? It's just
super interesting to kind of see what goes behind the scenes before electrical actually gets in. I think this was an episode that I think I learned a lot from it. So thank you, Byron, for kind of breaking it down. So for a while, I think hydrology was like a myth to me. I was like, what? Are we even doing
it's
it?
It's still mostly a myth.
Yeah, thank you, Byron. Appreciate you coming on.
Well, thanks for having me.
All right, and to all the listeners and viewers out there, please leave a comment, subscribe, share. Sharing is caring. Please do that. So we'll see you next time on the Sounds of Solar podcast. Until then, take care and,
hydrology.
Yeah, hydrology. And the sun is so powerful. We'll see you next time.
Peace.